Юрий Анатольевич, день добрый. Вас не слышно. У нас тут были какие-то перебои со звуком. Hello everyone. We have some technical issues, so please bear with us. We just need a few more minutes to through. So just please wait a bit.
Hello, do you hear me? Hello.
Yes, we can hear you.
I am very sorry. We are very sorry for some technical problems. And now let's start our today's lecture. Today we will consider some problems about power supply and power quality in industrial electrical networks, especially at mining enterprises. We will consider some issues about some technical issues about harmonics, about power quality standards, international standards, and we will tell about main consequences of harmonic presence, main negative effects which are caused by harmonics, and we will talk about main technical decisions some devices intended to eliminate harmonics. And now let's start. First part, harmonic disturbances in networks and their treatment. First of all, let's consider the phenomena of harmonic, the main harmonic quantities. You know that our electrical energy are transferred by means of fundamental harmonic, fundamental current, and fundamental voltage harmonic, which frequency is equal to 50 hertz in some countries and equal to 60 hertz in some other countries. If we have some harmonic, her frequency is equal to frequency of fundamental component multiplied of some number. For example, 2, 3, 4, 5, and so on. And when we have such harmonics in our power supply system, our waveform of voltage and current will be distorted, sorry. And such distortions is the main reason of some negative effects in power supply systems. And first of all, about quantities, harmonic order. It is the number of some harmonic. It's the some relationship between harmonic frequency and the fundamental component frequency. And also, when we want to know the whole information about harmonics, we need some spectrum. Yes, here you may see some example of such spectrum where we can find the amplitude of each harmonic which are presented in our power supply spectrum. And also we can express our distorted wave by means of the mathematical expressions called Fourier series as follows. You see some equation which reflects such Fourier series. And in common situation, we may have some DC component in our spectrum, which frequency is equal to 0. And other components are some harmonic components. Number one reflects the fundamental components. All other components are called high harmonics or simply harmonics. In all standards, in Russian national standards, in international standards, we consider the whole spectrum of harmonics above 40 order. After 40 order, some harmonics are neglected. And also we can calculate some RMS value of any distorted wave by means of some expressions. Here you may see the example of such equation, and we can calculate current, harmonic current, and voltage harmonic in our power supply systems. And also, when we talk about harmonics, we should consider some ratios, some factors which reflects the level of harmonics in our power supply system. Here we have two main ratios. The first is the individual harmonic ratio or harmonic percentage. It is the ratio of nth harmonic to the ratio of the RMS value of some harmonic component to that of the fundamental. This ratio is reflected often in percents as the percentage of any harmonics. And also we have sorry for some technical problems again, and also we have some integrated ratio, which called total harmonic distortion. Total harmonic distortion, which reflects the total harmonic percentage in our spectrum. Here you can see the expressions which allow us to calculate these factors. And these factors can be changed in the range of 0 and 1. And now let's consider some effects which are caused by harmonics. And here we have two main groups of effects. The first group is the instantaneous effects, which reflects some short time effects in power equipment, in power supply systems. And let's consider them. And the first group of effect is the vibrations and noise. Such effects are connected with the rotating fields and vibrations in rotating machines, and some electrodynamic forces produced by the instantaneous currents associated with harmonic currents. In power supply systems, one moment please, sorry, some pause. And now let's continue. And the second main group of effects are long-term effects. These effects are connected with the heating due to the additional losses in some electrical equipment, for example, in rotating machines and transformers. Also, such heating is applicable to cables and other equipment. And these additional losses includes an increase in RMS value of current for an equal active power consumed. It's are additional power losses in our power supply systems. Also, we should take into account some supplementary losses in transformers due to the skin effects, hysteresis, and eddy currents. All these effects are long-term because they are reflected in whole lifetime of our electrical equipment, such as transformers or rotating machines. Also, such effects are connected with the increase in the electric losses in the insulation with frequency in cables, in transformers, and also in capacitor banks. Also, such effects are extremely negative for capacitor banks, which intended to reactive power compensation. And when we want to know the level of such distorted current or voltage, we should use some ways to know the information about it. The first way is the measurement using some devices intended to give the true RMC value of current or voltage. Reconstitution on the basis of the spectrum provided by spectral analysis, some harmonic components, and estimation such spectrum from an oscilloscope display. And some general limits for some distortions for different types of electrical equipment. For example, for synchronous machines, permissible starter current distortions should be in range from 1.103 to 104%. For asynchronous machines, the similar distortions should be in the range of 105 to 305%. For cables, such permissible core shielding voltage distortions should be equal to 10%. Also, for power capacitors, current distortion 83%. And overvoltages can reach up to 10%. Also, for sensitive electronics, voltage distortion should be no more than 5%, and maximum individual harmonic percentage no more than 3%, depending on the type of such sensitive equipment. And also, we should know some information about international standards, international standardized limits. We should consider some standards from International Electrotechnical Committee. Here you may see the list of main standards for some technical areas. And according to the limits presented in these standards, we should provide some measures, some technical or organizational measures in our power supply systems to correspond power quality level to these standardized limits. And here you may see the example such limits for harmonics. Here you may see that all harmonics can be divided into three main groups. The first group is odd harmonics, non-multiple of third. It is the main group of harmonics caused by main types of non-linear loads, which we will consider later today. The second group of harmonics is also odd harmonics, multiples of 3, and the last group even harmonics, which are presented rarely because they are connected with some transient phenomena in electrotechnological power installations. And for each groups of harmonic, for each number, you may see the harmonic voltage in percents of from the fundamental component, and such limits can be used to maintain some technical devices to eliminate harmonics. And let's consider the harmonic generators, the main harmonic generators. The main type of harmonic generators is the non-linear load, with non-linear voltage current characteristic. The examples of such harmonics generators are static converters, the main group of non-linear load, earth furnaces of different types, lighting systems, saturated reactors, and other equipment, for example, rotating machines, which can generate some slowed harmonics and sometimes are negligible. And first of all, let's consider the main group, which is presented by static converters on phase networks. The main type here is the rectifier bridge and more generally static converters. We should know that here we may see some different configurations of such bridges. For example, grades bridges or some high pulses group. Here you may see the example of such structure. Here you may see the 6-pulse topology of rectifier, or called grades bridge in international literature. Here you may see the supply current and some phase current upstream from the delta star connected transformer supplying of this rectifier. And these rectifiers are the main reason of the harmonic presence. Here you may see the example of such harmonic spectrum of voltage and current. And what about harmonics? Here you may see the harmonic orders, which are defined by the number of rectifier arms. For example, for some bridge topologies, P is equal to 6 or 12 for 12-pulse bridge, and K is the some number 1, 2, 3, 4, 5, and so on. And now you may see that the main harmonics produced by such load are 5th harmonic, 7th harmonic, 11th harmonic, 13th harmonics, and so on. And also we should take into account that also we may meet the other harmonics which are caused by the asymmetry in thyristor fire times, in accuracy in thyristor fire times 2, inaccuracy in switching times of thyristors in power converters, and in other cases imperfect filtering. All of these factors should be taken into account when we analyze the harmonic spectrum from each harmonic generator. And also we should consider some more complex power converters, which includes mixed thyristor diode bridges, which can generate even harmonics. And also we should consider cycloconverters, dimmers, and so on, which have richer and more variable spectra than common rectifiers as the main part of power converters. Also, the main reason of such disturbance is the pulse weight modulation technique intended to control power converters up to 12 kilohertz and more. And here you may see that harmonic spectrum also defined by the topology of power transformer, which are installed between power supply system and our diode rectifier. And some topology can cause some phase shift currents, for example, for 5th and for 7th harmonic, connected with the way of connection of transformer windings, as you can see in this picture. Also, lighting systems, including discharge lamps or fluorescent lamps, can can be harmonics generator, and they can generate harmonics equal to third and more. And in such cases, such harmonic produces dangerous overheating of some phases connectors, which intends to destroying. And what about earth furnaces? It's the main type of electrotechnological equipment in some industrial enterprises, in metallurgical enterprises, and they includes some rectifiers and regulating transformers. And they generate a spectrum including odd and even harmonics as well as a continuous spectrum. This spectrum depends on the type of furnace, its power rating, and the operation considered. For example, melting, refining, and so on. And according to the results of measurements, you may see the typical spectrum of harmonics for some earth furnace. Also, you should take into account DC and SC furnaces. They have different topologies. DC furnaces includes some rectifier, and AC furnaces don't include some rectifier. They use only some earths to produce technology, and earths possess the non-linear voltage current characteristic, and that's why such AC furnace produce harmonics. And some problems with presentation. Also, we should consider some saturated reactors and rotating machines as the main reason of harmonics presence. The saturated reactors can be used for limit our voltages, and in some cases they can produce also harmonics too. Rotating machines, especially during the start time, can produce some harmonics. And such problems. And when we consider some rotating machines, when we have rotating machines, the harmonics which presented by them can lead to some continuous heating without faults, and in some cases malfunctioning of current relays designed to protect against insulation faults. And when we calculate some harmonics, we should have some calculation models, includes the source of harmonics and some impedance. And when we have transformers, power transformers, we also should model them according to our calculation method. And also we should take into account the reactance of short circuit level. It's one of the main levels, one of the main factors which influence on the harmonics presence in our power supply systems. And also, when we're talking about harmonics, we should take into account some resonance conditions. And some such resonance conditions can lead to some faults in our power supply systems, which can also the reason of some power shutdown and stop of main responsible equipment. And also in presence of capacitor banks, such resonance conditions can be very often, and that's why we should use some technologies to prevent such resonance conditions. And also we should analyze some impedance versus frequency curves to detect the frequency of resonance to eliminate some harmonics from this frequency. And we should know some basic equations to evaluate the resonance and anti-resonance frequency when we calculate some non-sinusoidal modes in our power supply systems. Also, we should take into account some more complex topologies with distribution networks, harmonic sources, and so on. And according to such topology, if we know the total power of short circuit level and reactive power of capacitor banks, we can calculate the anti-resonance frequency and the corresponding number of harmonics which connected with such resonance. And also we should take into account some technical devices to prevent resonance. For example, some filter devices. And also such filter can be based on the series resonance or shunt resonance. When we used active, inductive, and capacitance filter, which have the resonance frequency according to this equation. And also we can maintain such filter to displace some frequency characteristic to prevent such resonance conditions. And for this purpose, we should use some anti-harmonic reactors intended to eliminate some harmonics from resonance conditions. Here you may see the typical characteristic which reflects the application of such anti-harmonic reactor. And when we use such reactors, we also should consider some capacitors banks which can be presented in our power supply systems to eliminate reactive power. And also one of the main types of filter devices which are intended to eliminate harmonics are resonant shunt filters. Here you may see the main equation to calculate the resonance frequency of such filter. And such resonant shunt filters are widespread in our power supply systems. Also, we should take into account some damped filters and also active filters. And when we have several such filters which are tuned to eliminate some harmonics, for example, 5th harmonics, 7th harmonics, 11th harmonics, and 30th harmonics, we have group of such filter. Each filter are tuned to one harmonic. Also, we have some main characteristic of such filter. For example, its tuning frequency, fundamental frequency, and reactive power for compensation, which can be calculated according to the presented equation. And also, we have characteristic impedance, which can be calculated according to the equation presented in this slide. The quality factor, which also can be calculated for such filter, and the pass band in relative items, which illustrate the pass band which can be covered by such filter. Also, the resistance of the reactor, the losses due to the capacitive current as the fundamental frequency, and also the losses due to the harmonic currents also can be evaluated by means of the presented equation. And also we have more difficult topologies of such filters. For example, second order damped filter. It is more complicated topology, which also intended to eliminate harmonics. Also, they have the following properties: anti-resonance damping, reduced harmonic voltages, and fast damping of transients produced when the filter is energized. And here you may see such topology, which includes the additional resistor, which connected in parallel with the main filter. And such solution allows us to damp some anti-resonance conditions. And also such filter can operate in other areas of such characteristics, and in each area he produce different characteristics, which also should be considered when planning harmonic elimination devices. And also for such filter we can calculate the reactive power for compensation according to the similar equation, tuning frequency and fundamental frequency. Also characteristic impedance, quality factor, and other parameters similar to the resonance shunt filter. And also here you may see the comparison between the initial characteristic and the characteristic with resonant shunt filter, initial characteristic, and with second order damped filter. You may see that the total impedance is lower than with resonant shunt filter, which allows us to prevent some anti-resonance conditions with amplifying some voltage harmonic according to the very large impedance in some point of power supply systems. Also here you may see the more difficult topologies of such filters. For example, third order damped filters of other topologies, C-type filter and double filter. These topologies are complicated and intended to for application in different power installation according to the harmonic spectrum. But the area of application such filter is very small, because they are very difficult and they demands very precise tuning of each parameter, and that's why they are not so effective in a whole range of harmonics. And also we should consider some examples of harmonic analysis in some industrial power supply systems. The main diagram presented here. We can model some modes of these power supply systems without capacitor bank, with capacitor bank, and so on. And for each mode, we should model some spectrum and some harmonic impedances for each harmonics. For voltage distortion, for example, you may see the harmonic voltage spectrum, current spectrum in current load of capacitor, and resonant shunt filter tuned to eliminate fifth harmonic, and to damp filter tuned to seventh harmonic eliminations. And here you may see some example of such modeling which reflect some problems connected with the filters and capacitors in conditions of harmonic presence in power supply systems. For example, the spectra of the currents flowing in the reactors connected to the capacitors, the total voltage distortion at the capacitor terminals, and reactor manufacturing tolerance and means, and some spectra of the currents flowing in the resistors of the damped filters and their total RMS values, and also voltage and energy transients affecting the filter elements during energization. And also we should take into account some active filters and more complicated devices. Sorry for some again problems with presentation. Now let's consider another technical device intended to eliminate harmonics. The traditional solution includes the passive filters, for example, resonance shunt filters and damped filters. And the second part of our today lecture is intended to consider the active filters as the other group of harmonic conditioners, active filters, parallel active filters, and series active filters, and also we will consider some active rectifiers. The traditional solutions are intended to correct some impedances, some total reactances to eliminate harmonics, and active solutions intended to generate some current or some voltage, which includes the same harmonics or voltage or current, but with opposite phase, which intended to eliminate harmonics. And for example, we have active harmonic conditioners. For example, active harmonic filters, which are produced during several 30 years because of the typical characteristics of modern semiconductors in static converters, which gave us an opportunity to use such intelligent technologies in static converters to implement some harmonic elimination technologies. And for example, active filters, let's consider them. The main types of such filters are the shunt type filter and series type filters. The main topologies you may see here in this slide. Shunt type filter intended to eliminate current harmonics, and series type active filters is intended to eliminate voltage harmonics. And the main also such active filter can be equipped by the additional passive filters, and in such condition we have some hybrid topology of such filter. Also the similar devices called unity power factor rectifier or active rectifier, which intended to eliminate reactive components and maintain the power factor at the unity level to eliminate reactive power totally. And here you may see the main principle of such functioning in the example of PWM rectifier, and also you can see there some diagrams of functioning of such rectifier. Here you may see some pulse width modulation technologies and some harmonic spectrum of the current upstream of such single phase rectifier. Also, we may use three-phase circuits and other more complicated components. And let's consider the active harmonic conditioners technology, main technology. You may see that the base of such technology is the noise techniques, sound techniques, which are intended to eliminate some additional noises in microphones and other sound systems. We produce some sound which in opposite of the main sound to eliminate some additional useless sounds. And here you may see the such principle. We have load current, which we can analyze to detect the main harmonics, the amplitudes, the phases, to calculate them and to generate some compensation current, which includes the same harmonics of the same amplitudes, but in opposite phase to the initial current harmonics. And in point A, we have the sum of these currents, and as a result, source current can be purely sinusoidal waveform. But in the practice, we also have some little level of distortions in our source current by such level is very low, and this level is lower than standard limits for current distortion. And also such filter, depending on the type of installation, the place of installations, can function in some modes. Local harmonic compensation, for example, you may see here, global harmonic compensation, and some semi-global compensation. And it depends on the level of installation such filter. And here you may see the main structure of functioning of such filter. We have control and monitoring systems, reversible inverter, capacitor bank, input filter, and some generation of reference values of voltages or currents. Also, now you may meet in some scientific literature or technical literature a great amount of control methods of such filters, which are based on the power theories, current theories, and Fourier transformations, and so on. Also, we can have different topologies of such filter with inductive element and capacitive bank as the storage element, with different combinations of output filters. And also the main functions of control and monitoring systems of such active filters. The first function is the control of capacitor load. The second function is the regulation of voltage and generate some current to eliminate harmonics, or consume some current to charge of storage capacitor. And here you may see the two main methods of signal processing methods. The first type is the real-time method on the base of Clegg transformation and so on. The non-real-time method used for sorry, we have another problem with this presentation. Sorry, one more time, please. We have two methods. First type is the real-time method on the base of Clegg transformations, and the non-real-time method used based on the fast Fourier transformations, discrete Fourier transformations, and so on. And all these methods are used dependent of the load's parameters. with ultra-fast variations in harmonic spectrum and their slightly variables, and two such methods. And also, when we use such filter, we have some pure sinusoidal current. For example, here you may see some examples of application such filters. Without filter, total harmonic distortions equal to 80%. 80%. Sorry, another problems. Here's some examples. Total harmonic distortion equal to 80%. And with filter, such total harmonic distortion decreased to 4.6%. It's significant decreasing by means of implementation of such filter. And you may see that the total efficiency of such filters is more than for traditional passive filters. Here you may see the corresponding harmonic spectrums as a result of application of such filter. And here you may see that the harmonic components also decreased significantly. And other characteristics with or without harmonic conditioner, as you may see the total RMS value of consumed current also decreased approximately in 10%. And you may see that such active filter can be presented as the multifunctional device intended to imply the different functions for power quality improvement. And also you may hear another example of the application of such active filter and some other moments connected with such filters. Also you may see the examples of application of such filter. And now let's consider the combination of active filters and passive filters, which create some hybrid conditioners or hybrid filters. For example, here you may see some diagram to illustrate the application of active harmonic conditioner as the active part of our hybrid topology voltage active harmonic filter, and some passive filter connected in parallel with this active filter. And so you may see the voltage distortions and current distortions from the load. And some example illustrate the main hybrid topology. Also, you may find another topology which includes the series connected of active filter and passive filter, and how this topology are connected in parallel with some load. You may meet another different topologies of such hybrid filters. For example, here you may see the series parallel type of such hybrid conditioner. Also here you may see the voltage type of active harmonic conditioner and current type of passive filter, resonant shunt filter, for example. Also you may meet in more different topologies with with three winding transformer. Each secondary winding is intended to connect some filter parts of hybrid system. For example, here you may see in some problems again. Sorry. Here. When we have several windings transformer, the first secondary winding intended to connect active harmonic conditioner, and the second winding are intended to connect some non-linear load. Also, you may meet the current harmonic active conditioner, which connected in parallel with several types of passive filters intended to correct some canonic harmonics, for example, fifth harmonic or seventh harmonics. Such a topology, called parallel connection of active harmonic conditioner and passive filters, is very widespread in industrial power supply systems. When we use some passive filters to eliminate some character harmonics, for example, fifth or seventh, and the residual current distortions are eliminated by active harmonic conditioner of the decreased ratio and the decreased cost. And now let's consider some performances of hybrid structures. For example, here you may see the parallel series type hybrid conditioner and the several modes of its functioning: without filter, passive filters only, and passive filter and active harmonic conditioning. Here you may see some effects caused by the application of such topology. And another example with another configuration of hybrid structure presented here. Also, you may see the different modes of the functioning of such systems. And also here you may see some summary of advantages and disadvantages of different topologies of active and hybrid systems. For example, here you may see the series type filter, shunt type filter, shunt hybrid filter, and another hybrid structures of active filters. And here you may see some functions and some comparison between them in other application areas. And such tables will be useful to evaluate the advantages and disadvantages of each structure when we taking decisions to apply some topologies in power supply system. And the main reason of such topologies is the multifunctional systems. And for example, also we should take into account the point of installation of such active or hybrid device. And here you may see the different levels when we can install our filters. For example, at the main low voltage switchboard, sub-distribution switchboard, and terminal switchboard close to the load. For example, motors or some converter systems. Here you may see the global mode of correction, semi-global mode of correction, and the local mode of correction, depending on the place of installation of our active filter. And here you may see the main features of such modes. For example, local harmonic compensation, semi-global compensations. Here you may see some summary of advantages and disadvantages of each mode of harmonic compensation, for example. And also let's talk about some sizing of shunt type active filters. First of all, we should take into account the RMS current, which presented by this filter, band width, and its dynamic capacity. Here you may see the total current produced by such filter. Also, we should take into account the level of total harmonic distortions with and without such filter. And also we should take into account the residual level of total harmonic distortion for current and for voltage. And some application examples which reflects the main features of such active filters. For example, for protect some sensitive electronic technique from distortions from the networks. Also, some combination of shum-type active harmonic conditioner and passive components. In the area of motors with or without variable speed drive systems. Another example, here you may see the corresponding spectrum without compensation, with compensation, and other modes of correction. And the last part of our today's lecture is the overall power quality problem. First of all, this problem is connected with economic necessity to increase the competitiveness, the widespread use of equipment which is sensitive to voltage or current harmonics presence, and the opening the electricity market depending on the conditions of each country. And that's why we should take into account the power quality problem to plan to organize some technical or organizational measures to correct power quality level to avoid some negative consequences which can be reflected in our cost losses and economic problems. And also here you may see some objective of power quality measurements, for example, contractual application, corrective maintenance, optimizing the operation of electrical installations, statistical surveys, and all these tasks are connected with the overall power quality problem. Also, degradation of power quality level, origins, characteristics, definitions, and so on. Here you may see the main reasons of such poor power quality level. You may see that such events are connected with voltage dips, harmonics, temporary voltages, transient over voltages, voltage fluctuations, power frequency variations, and so on. Also, not only harmonics present a poor quality level, also voltage dips and interruptions, also one of the main problems in power quality area. For some equipment, any voltage dip, also small voltage dip can be dangerous for such equipment. For example, depth of such voltage dip and such duration. Here you may see some example of such voltage dip and its duration. And for each equipment, for sensitive or unsensitive equipment, we should have such characteristics for voltage dips and deviations, because such, for example, depth, for example, equal to 30%, will be not so dangerous for typical equipment, but for other sensitive equipment, such 30% depth voltage can be dangerous. And that's why we should take into account the type of equipment for which we are consider some voltage dips and deviations. Sorry for some problem. And voltage dips. And also we can have some types of interruptions: instantaneous, momentary, temporary, and sustained interruptions and over voltages of the different duration. And main origins, first of all, it's faults on transmission lines or distribution lines, also short circuits level, and some problems connected with the duration of such voltage dips. Also, let's talk about some regions. And some technical devices intended to eliminate such voltage interruptions. For example, one moment. Faults on transmission or distribution networks and short circuit levels and switching of large loads, long interruptions, sorry, the main problems, and let's talk briefly about other problems with power quality. First of all, some kinds of overvoltages, for example, lightning overvoltages, switching overvoltages, voltage variations and fluctuations, and unbalance. All these power quality problems also connected with overall power quality problem in our power supply systems. First of all, overvoltages are presented by some lightning processes, some switching overvoltages as the consequence of some switching of high power loads in power supply systems, and some effects of harmonics also, and some other effects of poor power quality. And also let's consider some technical devices intended to protect from such overvoltages and other power quality indicators. Here you may see some summary table which reflects the sensitivity to disturbance of each type of equipment: asynchronous motor, synchronous motor, actuator, speed drive, and so on. Here you may see the main power quality indicators, for example, voltage zips of different duration, over voltages, harmonics, and unbalanced conditions, and voltage fluctuations. And here you may see the information about which type of equipment are sensible or not sensible to some kind of disturbance. Also evaluation of some power quality problems according to their duration, parameters, contractual values, and measurement points. All these factors should be taken into account when we plan or organize our technical or organizational solution to raise power quality level according to the national or international standards. These factors should be taken into account simultaneously, not separately, because all of them are influence on overall power quality problem. Corrective maintenance also is one of the main stages of power quality raising. Some monitoring devices to control some power quality indicators and collection this data into data centers. Also power quality problem closely connected with the electromagnetic compatibility problem. which also are organized by international and national standards. Here you may see the example of such standards. And also we should implement some solution to improve power quality level for some tasks. First of all, to take preventive action when polluting loads are to be connected, ensure the installation conforms to a standard or to the power distributor's recommendations, and reduce energy bills, reduce energy costs for economical efficiency. And maybe today it's all information which I'd like to present you. And as the conclusion, I would like to tell you that the power quality problem is very wide. This problem is connected with the not only harmonics, but also other voltage and current characteristics. Such problem covers a great amount of devices and solutions to correct power quality level. And also we should take into account different types of harmonic generators, different types of filter devices to eliminate harmonics from different sources. Thank you very much. I hope that your course during summer schools at Mining University will be useful in your future activity. Thank you very much for attention and good luck. Thank you very much.
Thanks everyone, and bye. We will see you on Wednesday.
¿Qué? Personita, participantes. Ya. ¿Ah? 10. ¿Dónde nacieron? ¿Dónde nacieron? No, acá. Bien. Ahí tiene.